Okay, so right now I'm going to do momentum and impulse. And what I'm going to do right over here is I'm going to come back once I've done this video, and I'm going to put in the times and for each of the problems that I'm about to work. These are all the example problems, and they are in the PowerPoint. So if you go to Canvas and you look through and you find the PowerPoint for chapter 6. This is the second half of chapter 6. We're working on collisions. If you find that, you will see these problems. Okay, so if you want the problem statements, you can find them there. I will note that I did not update the page numbers on that particular PowerPoint. I don't have the energy right now. As you guys are probably aware, I have COVID at the moment. I don't know how long it's going to take me to complete this video. Who knows? I may do it and then get halfway through and get tired and go take a nap. I guess we'll see. I feel okay right now. Maybe a little bit of a headache, but nothing debilitating. All right, so start with example 1. Okay, we've got a 2 kilogram ball moving with a velocity of 5 meters per second due west. Okay, so let's see if we can't go over here. Let's see, we've got a 2 kilogram ball. 2 kilogram ball, and it's going this way, due west. What did it say? 5 meters per second, 5 meters per second. Okay, 2 kilograms. Okay, it collides with a stationary ball of mass 2.1 kilograms. So as I say, it can be helpful to have colors in this case. So here's our 2.1 kilogram. That way I can keep track of which ball is which. 2.1. Okay, after the collision, the first ball moves off at 30 degrees south of west. So that is the black ball. So you get black. So the black ball is going to move this way at 30 degrees south of west. Okay, so this is still the 2 kilograms. And the second ball moves off at 60 degrees north of west. Well, this is unusual. That's almost like an elastic collision, but whatever. 60 degrees. Okay, so this is our 2.1 kilogram ball. Find the speed of both balls after the collision. So here's our collision. Here's what's happening. And we are going to try to figure out the speed, the velocities of each of these balls. So what we're looking for is velocity. We'll call this ball 1, F. So that'll be like after the collision. And then right here, this will be velocity 2 after the collision. Okay, so, so then right here, this is V1 initial, is that 5 meters per second. Technically, it's negative, right? And then we got this 2.1 kilogram ball right here, which is not moving at all. So its V2I is 0 meters per second. Okay, so let's go ahead and just write all that down somewhere where we can refer to it, right? So I've got, let's see here. So M1 equals 2 kilograms. Man, my handwriting's terrible. I apologize, guys. M2 is 2.1 kilograms. Okay, V1I equals. Now here's where I'm going to do something that's going to be a little bit weird. I'm going to make my x coordinate this way, x, and make my y coordinate that way. Since both of these balls are always traveling to the left, I'm going to make x to the left positive, and that way I don't have to deal with any negative signs, okay? You are more than welcome to make x positive to the right. I just think in this case it's going to make my life a little bit easier. So V1I then is a positive 5 meters per second. V2I is, V2I is not moving, so that's initial. Remember, it's at the beginning of the problem, it's not moving, meters per second. Okay, and then I've got V2I, well, that's what we're looking for, and V2F, that's what we're looking for. Okay, I've mentioned that, or at least I hope I've mentioned that a lot of times I like to kind of arrange my data like this for these problems. Okay, so what we will note right off the bat is we've got 2 unknowns. I've got this unknown right here, and I've got this unknown right here. And so that pretty much tells me right off the bat I'm going to need 2 equations. Okay, so my 2 equations, probably this is a momentum problem. We've got a collision. So anytime you have a collision, you got to transfer a momentum, which means we need to be thinking in terms of momentum. So the momentum beforehand is the mass of ball 1 times the velocity of ball 1. Well, we needed a direction, right? X direction or Y direction. Well, let's start with the X direction. Okay, so the mass of ball 1 is moving in the positive X direction. Okay, so that's cool. That's all the momentum beforehand, right? Because ball 2 is not doing anything. Okay, equals. Okay, now I need the x direction velocity of ball 1 right here. So it's going to be m1 v1f. Oh, I guess this needs a little I, doesn't it? And then it's off at an angle, so I'm going to need the cosine of 30 degrees. Let's just call that, I don't know, we'll call that theta 1, and we'll call this theta 2, so we can stay in symbolic, at least for now. Okay, so this will be theta 1. Okay, and then we're going to, now some of the momentum went into this ball, and some of the momentum stayed in this ball, and then some of the momentum got transferred into this ball. So we're going to say plus m2 v2f, okay? But it's also at an angle, so we'll do cosine theta 2. Okay, keeping in mind that the unknowns here, this is what we're looking for, and this is what we're looking for. So I've got both of the things that I'm looking for are in my equation. So I just need another equation with both of those unknowns, and then we can solve this. So let's go ahead and do the y direction. Okay, and what's really nice about the y direction is that at the beginning of this problem, this ball is not moving in the y direction, so it has no y momentum. This one's not moving at all, so it has no y momentum. So the initial on the left-hand side of that equation is 0. And then the final is that basically these balls kind of get y momentum from each other. Basically, they push off of each other in the y direction. So one goes up, the other one goes down. So v1f, so we'll start with this with ball 1, m1 v1f, and it's got an angle of 30 degrees, so we'll do that sine of theta 1. Okay, and notice it's going downward, so I'm going to put a negative sign right there. So be very careful and don't forget that negative sign. And then we've got v2f going up, so it's going to be m2 v2f sine of theta 2. Okay, so hopefully you can see where those are coming from on this particular diagram. Okay, so now if we look down here, we're like, okay, cool. So now I've got two equations with the same two unknowns, which means I can solve these. So it's just a question of which one to solve first. This is the easier equation, so I'm going to solve this one first. Let's see here. So you notice that when I created this problem, whenever I did that, I gave slightly different masses, which means it can't cancel the masses out. I don't remember creating this equation, but this is something, or this problem, but this is something I would do to make you work a little bit for it. Okay, so let's go ahead and rearrange this. So I'm going to go, so let's see, m1 v1f sine theta 1 equals m2 v2f sine theta 2. Okay, and I'll go ahead and do v1f equals m2 v2f sine theta 2 divided by m1 sine theta 1. Okay. Yeah, that's fine. I think I'm going to arrange it slightly differently, though. v1f equals m2 over sine theta 2 over m1 sine theta 1 times v2f. Okay, I think that's just going to make things work out a little bit cleaner. Okay, so now we're going to go up here and we're going to plug that into this one up here. Yeah, I think it's okay. I think if we were to plug all those numbers in, for M1 and M2 and those signs, we would get a really nasty, we get, a decimal that we'd have to carry a whole bunch of decimal places. So I think I'm going to avoid doing that for now. Okay, so we're going to go up here into this top equation. I'm going to have M1 V1I equals M1 V1. Oh no, we have an expression for V1F. Sorry. So we're going to plug this in right there. Okay, so that's going to be M2 over M1 sine theta 2 over sine theta 1 V2F. Oh, well, I guess I need some brackets here. Don't cover up my little 1 there now. Okay, let's go back to black. And then we need to multiply that by cosine of theta 1. And then we're just going to add this expression in the end there, plus M2 V2F cosine theta 2. Okay, well, that's getting kind of ugly. We will note that this M1 and that M1 will cancel. This cosine and that sine will become a cotangent, but nobody really likes that. Let me just go ahead and clean this up a little bit. M1 V1I equals M2 sine theta 2 divided by sine theta 1. You know what, this is getting a little bit lost in the weeds here. Cosine theta 1 plus M2 cosine theta 2, and multiply that by V2F. Okay, so I think I counted for everything. Yeah, we've counted for everything. Okay, so V2F equals M1 V1I divided by M2 sine theta 2 divided by sine theta 1 cosine theta 1 plus M2 cosine theta 2. Okay, geez, pretty nasty. Let's go ahead and plug in. I'll go ahead and pause while I plug in. Okay, so I'm getting V2F equals 2.381 meters per second. Notice that we're going to have 2 sig figs in this answer. All these answers have, all the inputs have 2 sig figs, except for this, which the original 5 meters per second has 3 for some reason. Anyway, so we're going to keep this for now because I want to plug it into the other half. So where was that little equation that I had that I was plugging in? Oh, I guess I was right here, right? So I'm going to plug that in to right here. Okay, so again, I'll pause it while I plug in. I don't think you guys need to see me do the algebra. Okay, so I'm getting V1F equals 4.330. Okay, so again, 2 sig figs. So our final answer here is going to be V1F, V2F, okay, and I guess V1F will be 4.3 meters per second, and V2F will be 2.4 meters per second with 2 sig figs. Okay? All right, so that's example 1. I'm actually surprised I was able to do that correctly. I have a pretty bad headache. Okay, so there's number 1. All right, let's go down here to number 2. Okay, cool. If you can hear anything in the background, it's either Rocky or the fan. I apologize for those noises. The fan is necessary to mix the air in my room because the floor has no insulation, so my feet are freezing. But of course, the heat rises, so the heat that comes out of the central air tends to pool at the roof. Anyway, one day we can discuss the physics of your heating your house. Okay, find the recoil velocity of a 70-kilogram ice hockey goalie who catches a very small hockey puck slapped at him at a pretty high velocity. Assume the goalie is at rest before catching the puck, and friction between the ice and the puck goalie system is negligible. Okay, so this last statement right here is to tell you that this is isolated. And of course, we in this class, and in no high school physics class that I'm aware of, teach how to deal with a non-isolated system. I don't really understand why. I don't think it's that difficult. I think in fact, because it is, the systems are never truly isolated. I really don't know why we don't teach that, but we don't. So at this point, I'm just going along with the paradigm. One day, I'm sure I'll teach those. I'd have to make up all my own questions, but that's fine. Okay, so here we go. So we got an ice puck. Here's beforehand. We got the puck. It's cruising along this way at 35 meters per second. One nice thing to notice about this one's 1D, right? So the last one was 2D. 1D is a lot easier, always. Okay, so here's the puck, and it has a mass of 0.150 kilograms. Okay, and here's the goalie. He's much bigger. I can't draw a goalie. What is the goalie doing? Like I don't know what's going on there. Anyway, the goalie, he's got a mask. Whatever, he's on ice skates. This is the worst drawing ever. Doesn't matter. Anyway, his mass is what, 70 kilograms. Seems kind of small to me. Anybody know approximately how big a goalie is? Let's just say that, like, if he's 70 kilograms, you know, it's, I mean, a rough conversion from kilograms to pounds mass, which is not even a real unit, is about 2.2. So take that 70, multiply times 2, you get about 140. Add a little bit on there, so we're looking at about 150 pound goalie. It seems a little light to me. I've never played hockey, but maybe this is like, you know, the juniors league or something. Anyway, so this is beforehand. So this is before. And here's after. After, I don't know why my voice just did that, but I'm going to try to draw essentially the same goalie. Okay, but now he's holding on to the puck. All right, I guess pucks are always black. Maybe they're not. I don't know. And together, the goalie and they're moving this way at some speed. So this will be our V final, and that's what we're looking for. Okay. Now the total mass here now will be 70.150 kilograms, which is a very strange amount of mass, right? I would imagine that for this particular problem, you can almost neglect the additional 0.150 onto this guy. But we're going to go ahead and include it because there's no reason not to. Note that in this particular case, it's one dimension. But most importantly, we only have one unknown, so we only need one equation. And since it's 1D, the logical thing is to do the momentum equation in the x direction. I'm going to go ahead and make x positive this way because that's going to make my life a little bit easier. I'll draw y up, but it's not really important. We're not going to use it. Okay, so let's see here. So beforehand, all the momentum in the system is in this, right? Because he is not moving. I'm making a very sexist assumption that this is a dude, you know, which I don't know, whatever. I hope I don't offend you. So the mass of the puck times the velocity of the puck initial, all right? Okay, so that's all the momentum beforehand. Afterwards, all of that momentum is going to be carried in the puck and goalie, like, system, right? All of them together. Okay, so I'll call that the total mass, which would be the mass of the puck plus the mass of the puck plus the mass of the goalie. Okay, times their total final velocity, which I'll call VF. Okay, now notice in this particular case, this is the only unknown. We know the mass of the puck, it's given. We know the velocity of the puck initial, given. We know the mass of the puck, we know the mass of the goalie. So all we need to do is rearrange this equation and solve. So VF equals the mass of the puck divided by the mass of the puck plus the mass of the goalie, and VPI. Okay, I arranged it like this just because it pleases me. You do not need to arrange it like this if you want. You could have put the VPI on top there if that had been your preference. Okay, again, I will pause it as I plug the numbers in. Okay, so I get 0.074840 meters per second. And then I need to think about sig figs on this particular, and it looks like we're going to need 2 sig figs. So we're going to stop here with this guy right here. However, I do want to note that using meters per second when it's so small is kind of silly. So I'm going to change it to centimeters per second. So VF equals 7.5 centimeters per second. Okay, which basically means not a whole lot. He's going very slowly backwards, which of course you can imagine he's so much bigger. So that would be normal to expect that. The other thing to note, of course, is if the system remains isolated, he's just going to keep going sliding backwards, and that goal will score. In fact, any amount of momentum given towards the goal line will eventually make it in there as long as there's not an outside force. Okay, so in other words, he needs to, you know, dig his blades into the ice to keep himself from going backwards. Okay, any goalie knows that instinctively. You know, you never even think about it. I'm sure you just do it. Okay, so there you go. Okay, now we got another right. You know what? Let's pause. Let's end this one because it's going to take a long time to upload these, and we'll go one. I'll just do another. I'll do another video for example 3. Okay, cool.